Hi, this is Ramesh. I'm a student at Upgrade Triple ITB Data Analytics course. I'll be talking about a linear regression modeling concept of machine learning using a car sales case study. Right? So, as per this case study, a Chinese company wants to enter a US market, and for that, it needs to know how the sales of the car is happening there. I mean, how the prices of cars is influenced by the feature of the car, so that it could find a balance between cost and quality. For any analysis, we would need to understand business and data. Data can be clean or dirty, but before we proceed to build model, we need to make sure data is clean. Then only we would be able to prepare an effective model, right? Before diving into linear regression, let's understand what exactly linear regression is. So, say for example, we have two variables x and y changes with x, right? When y is represented linearly in terms of x, we call it as linear relation. And the way we find the linear relation is called linear regression. Right? So usually when we have continuous target variable dependent on independent variables and all these variables are numerical, we use linear regression. If we don't have all the variables in numerical form, we try to convert them to numerical form in data preparation section. We start building a model. At that time, we need to select most relevant feature of the system on which the dependent variable depends. And this is done using stepwise feature selection process. There are usually three variants to that: backward, forward, and both. I mean, including backward and forward, we have another form. Now, which one to select? That completely depends on the number of features and clarity we get from EDA and correlation table. But if the number of variables are more, in that case, using mixed stepwise process is much more beneficial, as the number of iterations to build the model is reduced. In case of multiple linear regression process, we see many independent variables are correlated with each other, right? This is called multicollinearity, where both independent variables which are dependent on each other are trying to predict the dependent variable, which is not recommended. Now, having collinear variable causes coefficient of significant variable to change signs also, and that would lead to very bad decision making. Among many processes of data analysis, model building is the step in which we try to find what all features affect the dependent variable most and what is the degree of their effect. Right? After data cleaning and exploratory analysis, we see the significance of each independent variable and correlation between them. If the significance of the variable is low, then it is eliminated, and if the correlation is high, then also it is eliminated. If the significance is high and also the correlation is high, then we remove it and see if there is any change in explaining the dependent variable with the remaining independent variables. And if there is a major negative change, we bring back that variable and remove others following the same rule. We do this until all the variables remaining in the model are most significant and they are able to explain the dependent variable pretty well. So a linear regression model is basically evaluated using R-square and adjusted R-square. R-square is a number which explains what portion of given data variation is explained by the developed model. Whereas the adjusted R-square basically penalizes the score if a particular variable is not contributing to the model. So say for example, we are going with forward stepwise selection process and we try to add new variables to the model, and that particular variable is not adding up to the model predictability, then the adjusted R square will be penalized. But if it is adding to the predictivity of the model, the adjusted R square will increase. So when we start building a model can grow very big, very complex, which we don't want. Right? So if a model can be explained using less number of independent variables with high significance, we can say the model is simple and it is good for our evaluation. Right? The first reason to have simple model is to avoid overfitting, and next is it allows business to concentrate on non-trivial issues only. Right? With model complexity, bias decreases and variance increases, and a good model tries to minimize both bias and variance. The inaccuracy of predicting almost same result on slight change of input to model is called model variance. So say for example we are developing a model and it is complex, and we want to do some change in the input of this model and see how the output comes out to be. So for a complex model, this output won't be same all the time. It will start varying a lot, and this is called the variance. And as the complexity of model increases, the variance also increases. Whereas the other way around, when the model is simple, the complexity reduces but the bias increases. So basically the model is now evaluated, or it is moved by only those small set of variables which are forming the model, and we don't want that also. For a linear regression, there are few assumptions made. Number one, there must be a linear relationship between dependent and independent variables. We can see that using a scatter plot. Right? Number two, multivariate normality. So multiple regression assumes that the residuals are normally distributed, because we assume the results to be normally distributed in a general world event. So if the errors are not normally distributed, that means the results are also not normally distributed, and the model will be skewed at some end, and we don't want that. Right? The third assumption is there is no multicollinearity. Right? So as we saw earlier also, if there is a multicollinearity between independent variables, then the predictability of the model is questionable. Right? So we check that using VIF. Right? And the fourth assumption is homoscedasticity. Right? This assumption states that the variation or the variance of error terms are similar across the values of independent variables. A plot of standardized residuals versus predictability of the model is questionable. The variation or the variance of error terms are similar across the values of independent variables. A plot of standardized residuals versus predictable value can show whether this point is valid or not. Okay. For a linear regression, there are few assumptions made. Number one, there must be a linear relationship between dependent and independent variables. We can see that using a scatter plot. Right? Number two, multivariate normality. So multiple regression assumes that the residuals are normally distributed, because we assume the results to be normally distributed in a general world event. So if the errors are not normally distributed, that means the results are also not normally distributed, and the model will be skewed at some end, and we don't want that. Right? The third assumption is there is no multicollinearity. Right? So as we saw earlier also, if there is a multicollinearity between independent variables, then the predictability of the model is questionable. Right? So we check that using VIF. Right? And the fourth assumption is homoscedasticity. Right? This assumption states that the variation or the variance of error terms are similar across the values of independent variables. A plot of standardized residuals versus predictable value can show whether this point is valid or not.